Welcome to the seminar series on sewer and pipeline engineering. My name is Bert Bosseler and I am the Scientific Director of the IKT Institute for Underground Infrastructure. In this session we will look at the so-called trenchless construction. This is the underground laying of sewers and pipes without digging large trenches. And this time we will look at the pipe jacking method and learn from our research results at IKT. First of all, I will explain the construction process itself. Then I will narrow down some technical tasks and risks that have to be solved in pipe jacking. And finally, I will focus on the topic of quality assurance, based on experience from one of our major research projects at the IKT. But let us start with the pipe jacking construction process itself. In pipe jacking, the pipes are lowered in a launch pit and pushed forward with the main jacking station. The first step is to install a pipe jacking machine, which we see here in the front. With a cutting tool at the so-called shield, the soil can be removed. It is then conveyed through the pipe string into the starting pit. The soil is conveyed, for example, with a flushing liquid through a transport pipe to a separation plant above ground. The actual pipe installation then functions in such a way that the pipes are installed one after the other from behind and pushed forward. Since the pipes are pushed through the ground, there are, of course, frictional forces. The jacking station then must overcome the resistance at the shield and also the friction between the pipes and the ground. In order to reduce the frictional forces, the diameter of the jacking machine is usually larger than the outside diameter of the following pipes. This creates an annular space between the pipes and the ground, and this can be filled with bentonite, so the pipe is lubricated and friction is reduced. At some point, however, when many pipes have been installed, the necessary forces become too great. The last pipe would be subjected to all the forces and would be overstressed. In this case, we can install intermediate jacking stations in the pipeline. With these stations, the pipes are then driven in stages. First the front pipe string is pushed forward, then the rear one, then the front one again, and so on. Finally, the presses of the intermediate jacking stations are removed and the pipes are pushed together. The jacking machine itself can usually be controlled directly at the front, or at a control and steering station in the starting pit, or above ground. The direction for the movement of the shield machine is then determined by the position of the shield. In the shield itself, they are so-called steering presses which help to position the shield. The shield can then be used to steer back to the target line again and again, even if the ground conditions change and deviations occur. Overall, we can summarize three main points for this method. Number one, the soil is removed. Number two, the whole thing is steerable. And number three, the procedure is manned. So we can work directly on the shield machine with personnel, for example, to remove obstacles or repair the machine. To explain the balance of forces needed for pipe jacking, we see here a sketch from a well-known textbook by Dietrich Stein. If we look to the right, we see there a large V for the jacking force. This jacking force is introduced into the pipe string in the starting pit. To generate it, we need appropriate jacking presses and an abutment. The abutment is needed to support the presses on the opposite side of the starting pit. The press forces must now be at least so great that we can overcome all the resistances in the pipe string. And these resistances are made of two groups, as we already know. Number one, the resistance in front of the jacking machine, so at the shield here it is marked with an S. This pressure must be at least so great that the ground does not collapse and that we can easily remove it. However, it must never be greater than the so-called passive earth pressure, because otherwise we push the soil further forward and there is uplift at the surface. The second resistance is the frictional force R. As you know, we have to push all the pipes through the ground one after the other, and this means that the entire outer surface of the pipeline must be slid past the ground. And this sliding creates friction and thus a corresponding resistance. Mathematically, this can be described quite simply by integrating the frictional stresses over the outer surface. The friction stress is theoretically the product of the friction coefficient μ and the vertically acting radial stress sigma r. Well, in practice, we do not know the exact values for sigma and μ at all points of the pipeline surface, so such an integral cannot be calculated. In practice, therefore, as we see in the equation on the right, we usually assume a mean value m as an empirical value for the shell friction, and we only estimate the whole thing. There are, of course, recommendations for m depending on soil type, depth, and of course the chosen lubrication of the pipe string. To reduce the frictional force, the pipe string is usually lubricated from the outside over its entire length. A bentonite suspension is used for this. This suspension is pressed outwards at regular intervals through the pipe wall into the so-called annular space. This annular space is a gap between the pipe and the ground. As already mentioned before, this gap is created by the fact that the jacking machine is slightly larger than the pipes. In the picture you can see the gap at the top and bottom of the pipe string. A special task is to make sure that this annular gap does not collapse. So the bentonite suspension not only has to reduce the friction, it has also to support the ground. This is also the reason why bentonite is used in the first place. Bentonite consists of clay minerals and water, and it is thixotropic and a typical supporting fluid in civil engineering. So far, so good, but what do we do if the jacking force is not sufficient to overcome the friction and shield force? We cannot increase the force at will. The first pipe at the jacking machine takes all the loads and must not be damaged. The solution is, as already mentioned in the introduction, to use intermediate jacking stations to distribute the loads over individual pipe sections. So what does that look like? Well, we can see that here. The intermediate jacking stations are installed when the jacking forces have reached the maximum that the pipes can withstand. The presses are then installed between two pipes over the pipe circumference. They are supported by the rear pipe and they push the front pipe further forward. In this picture we can see the process with several such intermediate jacking stations. Above at 0 we see all jacking stations, that is A, B and C. No press is extended in this state. A is the main jacking station, B and C are intermediate jacking stations, and D is the shield in front. In the first step, the intermediate jacking station at C is extended so far that the entire front pipe section is pushed forward by the length of small a. The shield then must remove as much soil as is needed for this movement. In the second step, the intermediate jacking station B is extended again by the same amount, so that station C can be pushed together again. In the third step, the main pressing station A is used. It pushes forward until all intermediate pressing stations are retracted again. The whole process continues until there is enough space at the main jacking station for the next pipe to be installed. And then it starts all over again at condition 0. As we can see, the whole thing can be easily dimensioned from an engineering point of view. However, this picture is a straight line jacking process without any problems with the ground. No obstacles that disturb and no steering curves at all. And that brings us to the second point. What technical risks do we have to expect in pipe jacking? To answer this question, let's take a closer look at the pipe jacking process in practical pictures. First of all, we have the starting shaft on the left with the jacking presses, a pipe and an abutment on the opposite side of the presses. The construction of the load transfer into the abutment and into the underground are special challenges. On the right we see the example of a soil excavation, here with a road header or selective cut heading machine. Normally during pipe jacking we have the shield there which rotates and excavates the soil. The soil has to be supported by the shield at the front, and in the annular space by the supporting fluid, the bentonite. But now we want to concentrate on the middle picture. We can see the pipe and the means for pressure transmission between the pipes. In the picture we can see how a wooden ring is mounted on the pipe mirror of the front pipe. This wooden ring has a very special task. It should transfer the longitudinal forces from the rear pipe to the front pipe. Such rings are therefore also called pressure transmission rings. They are located in every pipe connection. So let me summarize. Essential constructional elements are the starting pit or entry shaft, the jacking press and the pipes. The pressure is transferred in the pipe connections via a pressure transmission ring. And the soil requires support and excavation, and it produces friction. And in addition also groundwater can play a role. Well, maybe you have already noticed the soil, the pipe connections and the pressure transmission means are of particular interest to me, and there is a good reason for that. Because in pipe jacking there are not only straight line pipe routes. In this picture we see how the pipes lie in a curve. Such a curve is usually planned before and may be necessary. For example, if there are obstacles or if an undercrossing of a river is needed. And in consequence there are challenges. The pipes themselves usually cannot be bent around the curve. A jacking pipe should absorb jacking forces and therefore it is usually very stiff. Large pipes, for example, are usually made of reinforced concrete, so if the pipe is to be bent around a curve, all bends must be made in the pipe joint. However, this also means that in a curve the pressure transmission ring is very strongly compressed on one side. And at these points the stresses in the reinforced concrete are also very high. Any miscalculation or steering error can then lead to damage, such as spalling of the concrete. Here, for example, we see some damage scenarios from practice. Spalling at the joints, whether inside or outside the pipe. Cracks of smaller or larger width. All this makes us uncertain and we are looking for an explanation. And of course for appropriate countermeasures. An explanation for the high stresses at the edges can be found in the geometry of the pipe connection. The pipe ends lie parallel to each other. In the case of an angle joint, there is a linear distribution of strain in the pressure transmission ring. Depending on the material law, high strains then lead to more or less high stresses in the highly compressed area. If the material is plasticized, high stresses can be avoided. Against this background, it is important to have a precise knowledge of the material behavior of the pressure transmission means. And there are big differences. Here we see the stress-strain curve for 6 different materials. There are 2 curves for each material. The solid line represents the deformation at the initial load cycle. The dashed curve represents the deformation that occurs after 20 load cycles. Above we see the results for a chipboard. This behaves largely linear elastic with small plastic portions under repeated deformation. The curves for the 2 other wood-based materials, an OSB board in green and a plywood board in red, have a similar but a bit flatter shape. For the other materials, however, the curves look completely different. The pink curve stands for a material combination including plastic, wood and steel and has a band at about 33%. Then below, the plastic block with the brown line is relatively soft but shows almost no plastic behavior. It is largely elastic. And the lower dark blue line shows the behavior of the solid wood sample that breaks at a critical stress and then no longer shows any significant load-bearing behavior. And with solid wood, please keep also in mind the fiber orientation really makes a difference. Here we see a ring that was obviously assembled from 2 different solid woods with different fiber orientation. And this leads to uneven load-bearing behavior, because the strength in the fiber direction is much higher than transverse to it. And this brings us now to our research project, where we took a closer look at the quality influences and at the options for quality assurance. The first thing we did was to look at practical construction sites. This was done at a large German water association which had already carried out many pipe jacking measures, but was also planning many more. In doing so, we determined which conditions and scenarios usually occur in practice. Here we see an example route in which all relevant situations are combined in one route. The pipes come out of a starting pit on the left and they then pass through the route in several geometric situations. First of all, there is a straight line. The pipes are pushed in one after the other and therefore they experience a centric cyclic load according to the number of pipes. Even with the straight line, however, there are always deviations from the target route. This is the reason why the tunneling machine must be steerable. By steering the shield, the deviation is compensated, followed by the return to the target route. Afterwards, the pipe route continues straight on. The second straight line is then followed by a planned curve. Such curves are needed to avoid known obstacles or to follow the course of a road, for example. Finally, we come back into a straight line and finally the pipe jacking is completed. This sample route was a first important result of our research work. And this route was the basis for many laboratory simulations on a scale of 1:1. And one finding was particularly important for the simulation. We can see in the picture that all situations can be simulated well with just 5 pipes. The straight line, the steering correction and also the planned curve, all this can be ideally simulated with 5 pipes. And that is how we did the large-scale tests at my institute, the IKT. Here we see a top view of the experimental setup. The whole thing is called IKT Pipe Jacking Simulator. On the outside we have a massive steel vessel. This is the actual large-scale test stand at IKT. On the left, the pressure jacks thrust from an abutment onto the pipe string. The pipe string itself consists of 5 jacking pipes. Each pipe has a diameter of about 2 meters. On the right, the last pipe is located in an articulated support. The jacking abutment is connected externally to the test stand, so that the abutment forces can be transmitted into the test stand itself. But the most interesting element are the lateral forces. They are provided by 8 lateral pressure jacks. These jacks are connected to steel rings in which the pipes are held. Between the pipes and the steel rings, we placed special hydraulic cushions which ensure an even bedding of the pipe within the steel ring. And the rings themselves lie on Teflon plates so that they can be moved easily sideways. And this makes the purpose of the whole thing very clear. With the horizontal jacks, the pipes can be positioned in such a way that we can simulate all important pipe jacking conditions in the test stand on a scale of 1:1. This also means that we can traverse the sample route again and again in the same way and compare the results, for example for different types of pipe or different pressure transmission rings. After all, this is not possible in practice because the soil conditions in the route of the pipeline vary from side to side. In these pictures, we see how the test stand looks like in reality. In the upper left corner, the pipes are placed in the steel frames. Under the pipes and on their sides, hydraulic cushions are positioned as bedding. Below we see how the pipes are placed one behind the other and how they can be positioned with the horizontal pressure jacks. On the top right, we see our measurement technician working directly under the horizontal jacks. And below on the right, there you can see the main jacking cylinders. With these, we were able to apply jacking forces of 8 meganewton, which is about 800 tons. This is quite representative of a typical pipe jacking site and well enough for our sample route. Here at the top, we see the test setup and below it, the corresponding part of the route. And there is also a sketch for the structural system, which is simulated here. With a straight line, we started a total of 10 load cycles as average for the pushing of the pipe into the straight line. From the straight line, the route continued into the deviation from the target route. Then the steering correction, the return to the target root, and then the second straight line, a planned curve, and finally the last straight line. Of particular interest were the pipe stresses and strains in the planned curve shortly before the end of the pipe jacking route. In terms of statics, the curve is often the critical condition to which the entire system is dimensioned. That means the pipes and also the pressure transmission rings. Here we see a sketch that was usually imagined in the statics as a typical loading for a curve. Of course, before our results were known. The pipes are all evenly distributed in the curve, and as a bedding reaction it is assumed that the pipes experience an evenly distributed bedding pressure on the outside of the curve. This seems very logical at first glance, because if we press the string from the left and from the right, so the resulting force must go outwards. And an even bedding, well, that seems a quite natural assumption. But the nice thing about our experiment was that we could measure in the hydraulic cushions what really happens in the bedding. And of course, we and all the experts who accompanied the project expected the following. We expected that we would be able to measure a very even bedding reaction on the outside of the curve. Anything else would not be logical, at least we thought. Well, and then came the results. We can see very quickly that everything looks very different. The pipes are held on the outside, but this is especially true for the first and for the last pipe. The pipes in the middle, on the other hand, are held on the inside. That means that the whole thing actually looks like this. The pipes in the middle obviously want to pull themselves straight, and the outer support forces are only found at the beginning and at the end of the curve. But this also means that the pipes are under very different loads than expected. And in the first and last pipe connection in the curve, there are considerable transverse forces. Furthermore, the pipes are no longer evenly distributed in the curve. In the middle of the curve, the angle might be small, but in the other joints, it must be all the greater. The movement of the pipes and the gap in the joints therefore may differ from pipe to pipe. We could also say the pipe kinematics are not as ideal as we had imagined in the statics up to that point. This also means we must expect larger gaps in some pipe connections and therefore also larger stresses on the compressed side of the pipe. This was a very important finding, and it was incorporated into the rules and regulations and the safety considerations of structural engineers in Germany. Under such conditions, however, something else is also important. We now need to know even more about how the pressure transmission means behaves under extreme loads. Therefore, we have also carried out many investigations in this field, and it was particularly interesting to see how the various pressure transmission means deform in comparison to each other. Here we see test specimens of pressure transmission means which we subjected to typical jacking loads. 5 different load tests were carried out for each material, with 5, 10, 15, 20 and 30 megapascal compressive stress, each with 20 load cycles. The individual test specimens are shown in this picture, stacked on top of each other. 3 of the stacks are made of wooden materials, and the last stack on the far right is made of plastic, namely PU, that is polyurethane. Once a solid wood was tested, once a V100 chipboard, and once an OSB chipboard. OSB means oriented strand board. In all cases, the wood also deforms plastically. This also means that the wood adapts well to the concrete surface. In addition, wood has a low transverse elongation, so low lateral strains, which means that there are only small splitting tensile forces in the concrete. The plastic far right, on the other hand, is comparatively elastic. All test specimens have returned to their original geometry after being unloaded. However, the lateral strains of plastic are significantly higher. If we want to reduce the risk of splitting tensile forces, we have to place a sheet metal between the plastic and the concrete so that the concrete is not torn apart. This is a picture from a concrete pipe string. Here we can see how important it is that the pressure transmission ring can adapt itself elastically or plastically well to the pipe joint geometry. Spigot end and socket are obviously not ideally parallel to each other. The pipes are usually manufactured vertically with the spigot end pointing upwards. In consequence, the spigot end in particular can have an uneven surface. In our large-scale tests, we then looked in more detail at the stresses that occur in the pipe joints, depending on which pressure transmission material is used. For this purpose, we used the foiled sensor measuring system in the pipe joint between the second and third pipe. The picture shows the cross-section of the measurement joint. The foiled sensors are mounted in the spring line of the pipe and above and below it. The stresses were then measured continuously over the entire simulated jacking process. Let's now take a closer look at the results for the foil measurements in the left and in the right extreme of the spring line. Here we see the pressure distribution in the left and right extreme of the spring line, first a solid wood, then a chipboard and a polyurethane ring. The measuring joint has been pushed forward to point 1, which means that the first straight line has almost been completed. We see quite similar results for all pipe joints. The stresses are in the low or medium range and they are distributed quite regularly. Don't bother about the black bars, they are only failures of the measuring sensor. This result, of course, is not surprising because the pipes were pressed steadily straight ahead to the virtual location at point 1. So differences in stresses can only result from geometrical imperfections, in particular from the unevenness of the concrete surface in the pipe joint. Here we see the second rectangles and the stress distribution after passing the steering curve. So we are now at the location of point 2. With the plastic, the polyurethane, the measured values haven't changed at all. This material obviously behaved purely elastically in the curve and it must have returned to its original shape. With solid wood and chipboard, however, the situation is different. In the section where has been the inner side of the curve, the stresses are now significantly lower. Obviously, the wood has been strongly compressed and has undergone plastic deformation. In the subsequent straight line, the stresses are then transferred more strongly over the other areas of the pipe joint, over those areas that have not yet been plasticized and still act with elastic behavior. And here we see the results at point 3. That means after passing the second curve, the planned curve. In the following straight line, the stresses in the polyurethane are still the same. The material has again behaved elastically. In contrast, the wooden materials show a very interesting, at first surprising picture. Now the stresses in the opposite spring line area have also decreased. Obviously, in the second curve, the pressure transmission means was again pressed into plastic behavior and as such has been relieved from the load. However, the question remains, both springline areas have been relieved of the load transfer, so where are the loads being transmitted now? Well, the answer is simple. The loads are now increasingly transmitted via the crown and the invert of the pipe. However, this means that after a curve, now higher risks can be expected for the crown and for the invert. If they are subjected to higher stresses because of a rise in jacking forces, then this too can lead to cracks or spalling. So we have learned, the pipe string geometry is not ideal. Large angular displacements can occur during pipe jacking, especially in curves. In the curves in turn, the pressure transmission means are subjected to extreme stresses. So what does this mean in practice? Well, we have to follow the pipe jacking process with measurements. In this picture we see a typical pipe jacking route. From the starting shaft at the top, a route runs over 480 meters to the target shaft at the bottom right. The pipes have an outside diameter of more than 2 meters. Of the 480 meters, however, only 350 meters are a straight line. 130 meters are excavated with a radius. Obviously, the route is to follow the course of the road, as it has to remain in public ground. Since only one curve was planned, OSB rings were used as pressure transmission means between the pipes. The gaps in the pipe joints were constantly monitored in order to detect excessive stresses in good time. Here we see how the joint gaps were measured and registered with a measuring device. Generally, it is sufficient to measure the joints at regular intervals and check whether individual joints are angled more than others. And if you know the course of the deformation changes, well, then you can use a retained sample to determine at any time which stresses must actually exist in the wooden material and therefore also in the pipe. For longer jacking runs with alternating curves, it can also be useful to install a measuring sensor permanently. Here we see a measuring box for distance measurement, which is pushed into the pipe joint. For this purpose, a small gap was left in the pressure transmission ring before. Here, the measuring box is installed at the crown of the pipe, which is particularly useful for vertical curves, as high stresses can then be expected in this area. And this brings me to the conclusion of our topic today, pipe jacking. I think we have learned some interesting aspects. There are main pressing stations, intermediate pressing stations, and of course the pipes and the lubricant or support in the annular gap. We have to work with great forces to overcome the resistance at the working phase and the friction between the ground and the pipe surface. In the starting shaft we need an abutment and we have to deal with the soil and the groundwater. Quality assurance plays a particularly important role. I have presented some results of our research. We have learned that there is no such thing as ideal kinematics in a curve. We have to expect both large gaps and extreme stresses in individual pipe joints. The pressure transmission means then has a great influence on the load distribution in the pipe joint, especially when negotiating curves. And there are different materials for pressure transmission. For straight lines, wood, especially OSB, is an economically sensible solution. The material is cheap, adapts well to the surface, and has low lateral strains. When negotiating curves, however, an elastic behavior is required. Here the use of plastic can be useful. And finally, it seems a good idea to closely monitor the deformations in the pipe joint so we can detect risks in good time. Thank you.